Okay, good morning, students. This is going to be the part 2 of the analog design using LT Spice series. In the first part, we saw the design of a common emitter amplifier. In this, we are going to see CC amplifier, that is the common collector amplifier. Okay, in the demo, first we are going to simulate a CC amplifier and using LT Spice, and then we are also going to cascade our CE amplifier which we did in the last episode with the CC amplifier which we are going to learn now. So this cascade amplifier, cascaded, we'll see what is the advantage of cascading also. So you'll understand how some of the drawbacks of the CE amplifier is eliminated by using a CECC cascaded amplifier. Okay, this is the schematic of an CC amplifier. If you compare it with the CE amplifier, in the CE amplifier we had an RC here, out here, and then we had in the collector between the VDD and the collector, and we had taken the output, we had tapped the output from the collector of the transistor. In this, the collector is directly shorted to VDD, and we are tapping the output from the emitter of the transistors. Okay, so there are now this is the change which we have brought in. Okay, so now with this change, this is now the modified characteristics of the CC amplifier. Okay, it has got high power gain, voltage gain is less than 1, or it is, you can say, close to 1. So this CC amplifier is generally used as an buffer, right? So like I told you last time, right, not necessarily an amplifier will have voltage gain and current gain both together. It could have either voltage gain or current gain, but there will definitely be power gain. In this case, the voltage gain is almost 1, whereas the current gain is close to beta of a transistor. Okay, so there is current gain, there is no voltage gain, but there is power gain, right? Okay, now it has got high input impedance. Any other amplifier can easily drive this. It will not load the previous stage, so it has got high input. Low output impedance, it has got low output impedance. So what was the drawback? One of the major drawbacks of CE amplifier, that it could not drive low loads. Okay, the gain was proportional to the load resistance which was connected here, and for low load resistances, the for a low load resistance in the CE amplifier, the gain would drastically reduce because it is directly proportional to the load. In this case, the gain is more or less fixed. It is not proportional to the load resistance. So you can connect low out resistance also, and it has got a high bandwidth. Okay, so we'll see how to design these parameters, and but we'll first try and understand how this CC amplifier works, and then we will design like we did for the CE amplifier. We'll try and do some hand calculations and obtain the values of R1, R2 and RE, right? So these are the design parameters which an user will generally specify. Power supply is 20 volt, and for a CC amplifier, and nobody would specify gain and things like that. Okay, overall they might specify a gain which you will achieve through a CE amplifier, but this is the final buffer. Okay, this is going to drive the load. So what is important here is output swing, okay, and output resistance. So I have put an, in the CE amplifier case, we had an 50k load. Okay, so we neglected that, and RC, we took RC for all practical consideration as a load. In this case, the load is very low, that is 1k. 1k load, we have put here 1k load, so output swing is 3 volt. Okay, so these are the specifications. Now if you apply 3 volt across 1k, what is the expected current which is going to be flown here? 3 milliampere, right, 3 milliampere. So this transistor should be able to supply 3 milliampere, at least 3 milliampere of currents. Okay, now what should be the ideal voltage at this node? Like we did it for the CE amplifier, it should be at least, it should, since the VDD is around 20, it's 20 volt, this voltage should be 10 volt. If it is 10 volt, then there will be a proper swing of this voltage. Okay, so 10 volt. So when there is no input signal connected, you will find 3 milliampere is flowing in this path, and this voltage is around 10 volt. So 30 milliwatt of power will be dissipated in RE continuously. Okay, so similarly for the in the transistor, the voltage across the transistor, it would be again close to 10 volt, because 10 volt you have dropped here, 10 volt. And what is the static current which is going to flow here? It is again going to be 3 millivolt. So around 30 milliwatt of power will be constantly dissipated here. Whereas in the CE amplifier, we had designed it only for 1 milliampere. So that was not a power amplifier, that was not supposed to drive any load. So here you see the difference here. So we are going to dissipate large amount of power, 60 milliwatt. Okay, 60 milliwatt. So you have to see the specifications of whether this can handle such kind of power. In this case, double two can handle up to 500 milliwatt power, so this transistor is okay for it. Otherwise you might have to, for any, if you have to drive lower loads and take more currents from here, then you might have to change this transistor to some other transistor which can handle that kind of power. So in a CE amplifier you have to also cater for the power requirement. So accordingly the transistor has to be chosen. Okay, so this is the thing. Okay, now let's try and first find out the expression for the gain. Okay, so this is an CE amplifier. So let's just do the small signal voltage path. Okay, now here I am assuming RL is much lesser than RE. So for AC signal this capacitor is shorted, so RL is parallel to RE. And then so that's why this whole thing, I am, instead of these three components, I am only assuming there is RL. This is the worst case scenario. Okay, if RL is greater than, it is better. So we are going to tackle the worst case scenario, then automatically the rest of the parameters will fall in place. Okay, so these three components is only RL. So I am applying a signal V in here. So what will be the drop across the transistors? It will be IB into R pi. And what is this? So IE into RL. So this whole thing is become RL. So the current which will flow into the emitter is IE. Okay, IB will come from V in, IC will come from here. So they both together will form IE. Excuse me. So IERL is the voltage drop, and this is also the so if I replace it with 1 plus beta, and IB I take common. So IB into R pi plus 1 plus beta RL. And what is V out? V out is IE into RL. So V out again, IE I replace it with I beta plus 1 plus beta RL. Okay. Now if I divide these two equations, I get gain, which is 1 plus beta RL divided by R pi plus 1 plus beta RL. Okay. Now if I assume 1 plus beta RL is much higher than R pi, so you will get a gain of 1 approximately. Now see, in this, from this it is very clear that RL is not going to change the gain. The gain is more or less independent of RL. Okay, so this is the beauty of the common collector amplifier. Okay, another thing which we got to notice, the gain is positive. Okay, signifying that V in and V out are in phase. In common emitter we saw that the gain was negative, so the signal would get inverted. Here there is no negative here. Okay, it is 1, it is not -1. So these two will be in phase. Okay, another aspect which I would like to tell you is, see, there is no Miller effect here. So the capacitance between V in, there is no gain here in this amplifier when the signal is moving from here to here. Okay, so the capacitance is not going to get multiplied by the gain factor of 200 or 300 like in the CE amplifier, right? So the it has got a better frequency, better bandwidth. So but if you are going to cascade this, if a CE amplifier is going to drive this, the bandwidth will get limited by the CE amplifier. This will not deteriorate it. But if you are going to apply a signal directly here, from here to here, the bandwidth is very high, right? But this is not the input amplifier. Okay, so the CE amplifier will continue to restrict the bandwidth. Okay, by cascading these two stages, what we are going to achieve is we will be able to drive low loads. Bandwidth one we'll tackle it subsequently. Okay, so just understand, this amplifier in isolation has got a very good bandwidth, and it can drive low loads, and the gain is approximately equal to 1. These are the specifications. These are the characteristics of the common collector amplifier. Okay. This aspect, this is for theoretical calculations in many of the exams. These are generally asked, so I thought I'll cover this aspect also. The input resistance. Input resistance of a CE amplifier is, this is what? This is going to be an R pi, and what is the resistance which is going to be here? It is RL, but since the current out here is IE, so I got to write 1 plus beta RL, okay, and then parallel to R1 and R2, okay. So this is going to be the input resistance, right? Now I have seen, what you got to do is you just have to write the expression for V in, right? And in terms of I in is IB here. So you write V in is equal to IB into R pi plus IE. Instead of IE, I will write 1 plus beta IB, right? RL. So and then you divide the, and you do V in by I in, you will get this expression. Okay. So this is that. So you can say this common emitter amplifier has got high input resistance. So high input resistance is useful when this is being driven by some other CE amplifier. So we know the CE amplifier requires an high output impedance, and it cannot drive low output impedance. So you put this amplifier in between. So CE amplifier will see a very high input impedance. So the gain will not drop there for the CE amplifier. Okay. Now the output impedance. So how do we generally compute the output impedance? Is by putting a source at the output and see what is the current which will be drawn from this source. Now I have put a source, okay, V2 out here at this port. So it will have two currents. One current it will be through RE, and the other current will be through IE. So I can write this current V2 divided by IE plus IE. I0 is the current which is being supplied by this source. Okay. So this I have written as 1 plus beta IB, IE. I have replaced it with, and then IB I have written as V2 divided by R pi. Why V2 divided by R pi? What is the voltage across this? The voltage across this is V2, right? This is ground out here, AC ground. This is an AC equivalent circuit, so I have removed all the DC components. Okay, so this is the ground out here. Okay, so this is going to be the ground out here, because you have a source out here, right? So this is, I'll ground this, okay, because I'm applying a voltage here and this capacitance, so that ground has come from this point. So this is become, it is not that you should not consider R1 and R2. Okay, okay, sorry for this. Okay, here, because this capacitance is going to be grounded, this source is also going to be grounded, so the ground has come from here. Okay, so this is okay. Now you have V2 divided by RP, V2 divided. Now I am going to introduce a new term where RE, that is known as the emitter resistance, and as we see into the emitter of a RE, which is R pi divided by 1 plus beta. Okay, so now R out is equal to RE parallel to RE, that you get by dividing V2 by I0, right? So you will get 1 by RE plus 1 by small RE. So this is the output resistance. So this is very low, right? So that is R pi is in 2 kilo ohms to 10 kilo ohms, whereas beta is from 100 to 200. So you'll find this is coming in ohms. That is why we say that the common emitter has got a low output impedance, and low output impedance allows us to drive low loads. Okay, so that is about the common collector amplifier. Okay, now let's see, do some hand calculations. These are all rough calculations, how to arrive at the values for this R1, R2 and RE. Now we say the output swing is 3 volt. This is what the designer, the user has specified. Okay, I want a 3 volt output swing, and my output load is going to be 1K, right? So IL obviously will come as 3 milliampere. So this voltage across this RE, now it should be 10 volt. I said that, so that it is in, if it's in the midpoint, it is better. It can go to 13 volt and 7 volt. Output swing will be symmetrical across this. So you will get the maximum swing when we have this point as 10 volt. So for this 10 volt, we have the bias current of 3 milliampere requirement. So we get it as 3.3k. I take it as approximately as 3k. So this resistance value is now fixed. Okay. Now what is the value of VBB? Like last time, how did we do? We assumed ki this voltage plus this voltage. We took this voltage here. It is 10 volt in this case, and 0.7 volt here. So approximately 11 volt here. And why these 3 volt? Okay, because here we don't have small signal. We have a large signal out here, right? This signal can go up to minus 3 volt also, because this is a power amplifier, right? So this signal is coming after the CE amplifier. Okay, so this signal can go as low as minus 3 volt. So you have to cater for that also. So I have put another plus 3 volt out here. Okay, so that this is at 14 volt. So if it is at normally at 14 volt, this can go up to 17 volt, and it can come up to 11 volt. When it comes to 11 volt, still this transistor will be on, because this is around 10 volt, and 0.7 volt will still be available here. So you understand what is the logic of putting this 3 volt additional here. So 14 volt. Okay, now this is the voltage 14 volt available. What is IB? Like this is 3 milliampere, which we have decided in this branch. Okay, so divided by HFE, so IB is 3 divided by 50, right? So now what will be R1 and R2? Like we said, ki this particular branch should be able to cater, we should generally design so that at least 10 times of the current which is going in IB should flow here in static conditions. Okay, so 10 into 3 milliampere by 50 IB, this is 350, this 10. Okay, so if you do 33k, so the total resistance R1 plus R2 has to be 33k. So what will this ensure? Ki okay, at least 10 times of the IB will be flowing in this path. Okay, once you know R1 and R2 as 33k, and we know this voltage requirement, biasing voltage requirement is 14 volt, we can compute the value of R2. Okay, and we can also compute the value of R1 with these two equations. So now we know the value of R3, R1, R2, and RE. So with this we can proceed, and we can make this circuit in LT spice, and we can. Okay, now to summarize, this CC amplifier has got high power gain, high voltage gain is slightly less than 1. It has got a current gain which is equal to close to beta, high input impedance. So high input impedance will allow it to be driven by an CC amplifier. Low output impedance, this will help us to connect very low loads. We have designed it for 1k, but in the simulation we'll see what to do if you have to drive even lesser load. That I will explain you during the demo. Okay, now let's go to the demo portion. Okay, this is the CC amplifier as per the design what we did in the theory part. I'm not going to draw it and show you, because that I have already done in the previous episode. Okay, so this is 10k, 23k, 3k, 1k. This is as per the design what we have done. Okay, now the change out here is, now I am giving a large signal here. So amplitude is 3 volt. Okay, no, unlike 10 millivolt which we gave. So output also we should get close to 3 volt, right? So let me do a simulation and show you what happens. Okay, so let me plot Vs and let me plot load. You see, both are almost the same. So the gain is approximately equal to 1. So this is how an C amplifier works. Now, okay, but but this is still be considered as an amplifier. Why? Because it's a power amplifier. There's an improvement in power. Okay, so obviously the power cannot be created or destroyed. So where does that additional power come? That additional power is taken from the source, from the VDD, right? If you see the power which is drawn from the from this source is very minimal, whereas the power out available at RL is large. Okay, it is large because of the higher currents, and that extra power, okay, it's not created through magic or something. It is been That power comes from the VDD which is connected out here. So let us just plot the currents and see. So this is the way you're going to plot the current, right? So let me delete the unwanted waveforms. Okay, and let me plot this current. Let me put it into a new add plot panel. Okay, let me take the, this is IV2, V2 is this, right? So let me take this into, so what is the current? It is around 450 micro. So in this range it is around 450 micro. So this is the currents, 450 micro to 540 micro. This is the input current. And what about the output currents, right? See, the output currents is in milliamperes, right? So almost you can say 1,000 times, close to 1,000 times more currents, or maybe that, close in that order. So you have a huge current here. So that is why this is known as a buffer or a power amplifier. Okay, whereas the voltage gain is almost one, whereas there is huge power gain. Okay, the second aspect which we want to check is the bandwidth. So let me go to AC analysis, make it as decade. Let me plot 10 decades. Start is 1, and this is going to be 1G. Okay, now let me run the simulation. This magnitude is going to be 1, since we have given 1 amplitude there, and we are going to plot this magnitude. So if you see, it's just going straight, the huge bandwidth. So let me further change this to 100G. Okay, and run it. Okay, so you see, we load, okay, here the bandwidth is more than 1 gigahertz, right? You understand the, from the last time when we do, let me cut the unwanted waveforms. Okay, let me add a new page, add plot, and let me take this for more clarity. Okay, this is the gain plot, and this is the phase plot layout. If you see last time, if you remember, or you can go and refer back to that CE amplifier, around after, soon after 1 or 10 megahertz, this started dropping. So the bandwidth was very limited for an CE amplifier. Here you see the bandwidth, it is almost more than 1 gigahertz. Okay, till more than 1 gigahertz it's 0 dB. Obviously it will be 0 dB because the gain is 1. But the bandwidth, like how do you calculate the bandwidth? Like I told you the last time, if you got to go put an uh, marker. Okay, so this marker I am going to put it at, since it is 0 dB, I can go to minus 3 dB and check, right? So this is minus 3 dB. If you see here, minus 2.8, minus 3 dB, right? So this is minus 3 dB. And what is the frequency? 3.9 gigahertz. So it is got at 4 gigahertz of bandwidth. Okay, is it okay? So this CC amplifier has got a large bandwidth. Okay, let me close this. Okay, now let me come back to transient analysis. Okay, now see the fun. Now let me further reduce the, like I can go to 50K. Okay, let me first revert back to the 1K thing, and then we run a simulation, and then we are going to plot the output, you see a 3 volt output is available here, right? Okay, we have given 3 volt here, we are rotating for 1k. Okay, let me change this to 50k. Okay, and now I'm running it. See, the gain is not changed, so I can say the gain is proportion is not proportional to RL. Okay, now let me change it to near 100 ohms. Okay, so 100 ohms is a very very low load, right? So I'm going to run this. So now you see what is the problem. It is getting clipped. Okay, 100 ohms. Okay, with 3 volts it requires large current, right? 3 volts, if I have to drop 3 volts across an 100 ohms, I have to this transistor is not able to provide that amount of current, okay, to drive these 100 loads. So because we started the calculation assuming 1 kilo load resistance, right? So but here we are trying to simulate it with 100 ohms obviously, so this is not able to provide the current. So to provide the current, what is that we got to do is, see, and you can do hand calculations, but once you know the theory, and you'll be able to do it, in this also you got to increase this base voltage so that it produces more current, right? So I'm just going to increase it to 30k. Okay, I've increased it to 30k. Now more currents. What will more current? More current will mean more drop across this resistance. Okay, but I want it to remain, and I don't want to shift the DC operating point from here. Again, it might get clipped. So let me read. So since it's more current, but I still want around only 10 volt out there. So let me reduce this resistance at 20, 200. Okay, and let me run the simulation. See, okay, again you are getting it. So this is how, see, for different load conditions different. So if you are going to design it for a 100 ohm resistance, so accordingly these values will change. Okay, but if you see now, if you do it like this will constantly sink more current, and it will get heated up and more power will be consumed. So you have to be judiciously choosing these values depending on the max load conditions, right? If you're not going to have a resistance which is less than 1k, then you might accordingly design this and keep the minimum power requirement here. Okay, so now you'll also have to see, okay, whether in this particular condition, whether this particular transistor can sink that much current and can it dissipate that much amount of power. So these are all the design issues which you have to be careful with. Okay, so now let me get into the cascade stage. Already, just to save some time, I already CE plus cascade stage. Okay, now this was the amplifier which we had designed last time, CE amplifier. Okay, it had good gain of around 300, but the problem was it had a poor bandwidth, and also we were not able to connect low loads. Okay, we had connected a load of 50 kilo ohms, very large load. Now we'll see, we have cascaded this with this. So now we'll see whether it is going to give us the same gain even for 1k. Okay, so let me run the simulation and let me plot V in and let me plot V out. See, so I am getting a huge gain even for 1k, right? It is lesser than what it was only for pure CE, because in this case if you see uh, this amplifier we had connected 50k earlier. Now this is going to see this R1 parallel to the input resistance. Here it is only 10, and here it is 23, so it is close to 8k or something. But still, if you see, it is able to drive a 1k, and we are able to drive a very low load of 1k and still get reasonably well voltage gain, right? So if you have one amplifier cascaded, CE amplifier cascaded with CC amplifier, the advantage what we now have is we are able to drive low loads also without significant drop in gain, right? If you want to have much higher gain, then you can have two stages of CC amplifier and then drive this CC amplifier. So I mean, whatever gain. So for the gain, you can have one CC amplifier or two CC amplifiers cascaded. Get the required gain first, okay, to slightly above what is required, and then because there is going to be a slight drop when you connect this amplifier, so you have to get it. Say, if your gain requirement is 300, so maybe get it to 310 or 320 by using one CE amplifier or two CE amplifier cascaded to each other, and then finally to drive a low load we can use an amplifier which is CC amplifier, wherein you can connect low loads. Okay, and finally I just wanted to show you one more thing, which is right. So these things also you should know, that the voltage available out here in the CC amplifier was 8 volt, right? Around 8 to 10 volts was available here in the CC amplifier, right? So then what did we do in the cascading? We used a capacitor to decouple that DC voltage, and then again used two resistances to bias this CC amplifier stage. So this is a CE amplifier and a CC amplifier. So we can also, by judiciously biasing this operating point. Now this operating point, I have biased it slightly above. I have brought it close to 14 volt. Okay, by changing the values of these two resistances. Right here it was 10K earlier. So if I put 7K, what happens? The IR drop across this will reduce. So this operating point has moved up. Okay, it has moved up from the earlier 8 to now it has probably come to 11 or 12 or 13, 14, right? So with that, what has happened? So I have removed that coupling capacitance and the two bias resistance for these two transistors. So now directly I am coupling the output of this stage to this is through a CC amplifier. So I can run a simulation and see what happens. See, you are still able to get a high gain. So those two resistances have been two resistance and one capacitance has been avoided, and we have coupled it directly out here, right? So this has simplified the circuit here. Okay, so now there is only one drawback in this circuit, that is the bandwidth is very limited. Okay, okay, let me see. Let me see analysis. Okay, you see again the bandwidth is limited by 1 megahertz. Around 1 megahertz it started falling, right? This has got a higher bandwidth, but this has got a very lower. So the input signal which is coming here is getting at a high frequency signals which are coming here is not is getting attenuated in this stage. This is not able to amplify the high frequency signals, that we said because of the Miller effect. There is a drawback here. So in the next tutorial we'll see the third kind of amplifier, which is known as CB amplifier, and then we will try to tackle this, how to remove this, how to improve upon the bandwidth of this amplifier also. Okay, so that's all for today. Thanks a lot.